Yes, hi again, I am Altan. And I'll talk to you about my work in implementing the LDBC SMB BI benchmark for our, database system.
This is the demo effect. This should be good now.
All right, I'll tell you a bit about our work on implementing the LDBC BI benchmark for our database system Umbra. So I work at the Technical University of Munich under Thomas Neumann on his database system Umbra, which is a very fast relational database management system. And as you all know, the LDBC social network benchmark business intelligence workload is a graph workload, which was mainly measured with 2 graph and 1 relational system, and we are the relational system. So what we did was we took the graph queries that were already running on the graph databases, and we converted those to SQL, just any SQL that you know, and that is compatible with Postgres. And it turns out we are great at executing those queries that were originally meant for graph benchmarks, including the shortest path queries. So we are in a good place, but we still have a long way to go. So I'll talk a bit about this. And if you want to test these queries out for yourself, email me, I'll send you an Umbra binary, or if you want to do a quick test, we also have the LDBC queries available on our web interface where you can execute those with some sample parameters and see our query plans and all the details. So a relational database is great at executing all the various graph queries, including the shortest path queries, which is kind of weird, kind of unexpected initially. So what's going on here? Do we have an implementation where we simply cheat and check if the query is LDBC 19 and then execute the C++ implementation behind the scenes? No, of course not. We simply take in the SQL, process it, and execute it, and it seems we are still fast. But before I kind of talk about how we achieve this, let's look at the graph perspective. So what did the graph databases, so what's the graph way of modeling the world and understanding the world and executing it afterwards? So I looked at so to find out how one views graph workloads and how one designs graph workloads, I looked at the M4J's documentations, and what they say is that they navigate deep hierarchies well. They view the world as a bunch of connections and they navigate deep hierarchies well. So now the question is, what is then deep hierarchies? So let's say that we have this person, Altan, we know Altan, and we want to ask some questions about Altan. We wanted to find out, okay, who is Altan's cousin's wife's fish's, what is Altan's cousin's wife's fish's colors red component? So we navigate a whole bunch of hierarchies, navigate a whole bunch of connections, and we might even ask something crazy, like we might ask, okay, what is Altan's third cousin's wife fish's colors red component? And if you're going to ask a wide range of queries with deeper hierarchies or shorter hierarchies, then navigate such queries where it's not clear how deep you want to go, then a graph database might be right for you. But like, let's ask the question, like this might even go deeper and be even more convoluted. So let's ask the question, okay, I asked this query, Altan's cousin's wife fish's colors red component, but this query is slow. So what can I do? Can I like put more computers onto it, put more processes onto it, and have it be faster? Well, this is kind of difficult. Even if I split this query, even if I split this query up in the middle, right here between like, so if I say, okay, one computer can compute the fish and the other one can take the fish and compute the red component, well, this doesn't work because I need to know the fish before I compute the red component. So all these operations here have dependencies. So in order to compute this, you have to compute it one after the other, one step after the other, which means that looking at the world this way is not necessarily scalable. What would be scalable? So again, let's focus on a specific step. So Altan's cousin, we find out who this cousin is. Well, But the question is, what would have been scalable is instead is if we didn't focus on a single person and its connections, if we instead said, okay, let's take a whole bunch of people, millions of people. And we also looked at our edges as not single edges, but a whole bunch of edges, a set of edges, cousins of people. And then we combined them. What's the word for it? We joined these two. That would have been a scalable way of executing this query, because as we all know, with joins, and here we have a relation of people, relation of cousins of people, so sets of huge sets. And if we join these, this is a scalable operation that has been researched in quite strongly in our community. So, but if we start looking at the world this way, we are now thinking with relations instead of graphs and connections. So relations, thinking about relations and instead of graphs, is about creating a scalable model of the real world and then executing it. And it is well known that SQL is embracing the parallel. And why? Again, because we are working with big, huge multi-sets of data, and we are thinking of operations that we are applying to these big, huge multi-sets of unordered data. And this allows all our operations, well-known operations such as join and group by, to be scalable. And the point is, again, depth is not scalable. Depth is difficult to scale. However, breadth, large sets, that's scalable. So in a sense, I have a workload. Can it be scalable? I have a query. Can it be scalable? Well, can you express it in relational algebra? If yes, then I can confidently answer most likely yes. If not, you might have to do some extra work, which many databases currently are potentially not doing. So how did we scale the LDBC BI queries? First of all, we expressed them in relational algebra. In SQL, the standard way to express relational algebra, and we tried to eliminate depth as much as possible and increase the breadth. Think about these sets rather than the connections. And a really simple example as to how we did this, and there are more examples, but a really simple example is in the LDBC BI data set, we have a whole bunch of comments and posts and forums. So how is the structure? So we have a forum. If someone goes and posts a post in the forum, and this post receives a bunch of comments, and in the end, we get a hierarchy of comments that reply to each other. But if we were to ask something like, okay, what is the average number of messages per forum, or average number of comments, either comments or posts, then we essentially either we have to go and navigate this entire hierarchy for every comment or navigate down from forums. So this is depth. This is not necessarily scalable. What happens if if I have O of n comments all replying one after the other, giving me one long chain? Horrible. So what we instead do is, and this is a simple change in the schema, for every comment, we pre-compute their root posts. So this navigation operation becomes O of 1, which is possible to do in the LDBC BI workload simply because there are no link cut operations. What does that mean? So there are no operations where I take a comment, take a tree of comments, cut them up, and place them in another form. That doesn't happen. When you delete a comment, all the sub-comments are deleted. So there are no proper link cut operations. So we can just keep this information computed once and maintain it relatively easily. And one interesting thing is, this doesn't just improve the scalability in the simple sense, as I described earlier, by removing the depth. It also makes it much easier to estimate cardinalities, because looking at the relation of comments or messages, we have a column there that describes their root post. So looking at simple statistics of the relation can almost give us pretty good approximate results on the average number of messages per forum. So by simplifying the schema in a normal relational sense that every relational database manager would do, we simplify the query, speed it up, in both its execution and in its cardinality estimations. So we talked a bit about this small optimization we did and how Umbra essentially, how it's easy to attack relational queries to make them scalable, and how it improves our queries to eliminate the depth. And now I want to talk a bit about how you could beat Umbra. So please don't tell my professor that I'm telling you this. He's here, isn't he? Oh no. But I'm going to give you some tips and tricks on how to beat Umbra, how to beat this really fast relational system. So first of all, I split this in how to beat Umbra into 3 different categories, which are the main components of the Umbra system. So Umbra has an execution system, which is essentially the operators and their implementations. So our execution system is pretty good. And what it does is it takes in SQL, generate optimized binary, and the assembly you get in the end is essentially the same or better assembly than you would have written it yourself. Like, this is pretty much super hard to optimize for, like, by working on it. It's really hard to get it fast. So it's hard to expect like 2x, 5x, 10x improvements here. And we have highly scalable algorithms like worst case optimal joins. And as I said, we do JIT compilation of queries, and we are also scalable due to our Moseley parallelism approach. But we are missing a few graph algorithms, like shortest path algorithms, native implementations. We implemented them with pure SQL for this benchmark for now. But this is not likely to improve by large margins our execution engine, other than a few graph algorithms we might implement. However, our optimizer is still pretty good, but could use some improvements. Why is it pretty good? Well, we are able to, our optimizer does rule-based optimizations and then more holistic join ordering optimizations that are attached to it. So, but one important thing is we unnest all kinds of queries. So in SQL, you can write correlated queries, which are generally quite slow to evaluate because they're usually implemented with nested loops. So it could turn out that it's n squared, the execution of correlated queries. By unnesting arbitrary queries, we allow our great execution engine to be great at executing queries with low complexities. And we also have great join ordering algorithms. We do adaptive optimization that scales to many, many, many joins. However, our rule-based optimizations, unlike our holistic join ordering, is not always consistent. The order of application of these rules matter. And even if you write 2 queries that are semantically equivalent, their execution times might be different, which says that there is a potential for improvement here. And there's one more section of statistics. So the statistics provide the optimizer with the information it needs to pick the best plans, and the optimizer provides the executor with the plans that it needs to execute. And our statistics are great on Bayes relations, and we also recently saw great improvements in estimating group-wise results after selections. However, we are great at estimating keys because they are simple, but if an attribute is not a key, we are not always that good. So it's not necessarily always start crying, but it's sometimes not that great. But statistics is an exceptionally hard problem, but these affect optimizations, and these in turn affect the execution. So they are, in a sense, the most important part of the database, but also the weakest. So there's lots of potential for improvement here. And to essentially conclude, I want to leave a small note about the BI SQL queries. We start, unlike many other benchmarks, we actually could write the SQL queries here ourselves and improve them over time. And the queries did change over time. If you go to the GitHub page for the queries, you can see how they have improved. And we have seen over 10x improvements gained by rewriting the queries. And the thing is, if we wrote the queries to give the same results, the optimizer should have done this, the things that we have done manually. So if you're interested in optimizer research, please don't just check out the final version of the queries, go back in the Git history and look at the queries before they were optimized. But if you're interested in execution, likely the last versions of the queries would be the most interesting for you. So this is it for me, and I'm open to any and all questions.
Thanks, Altan. A question from Leonid.
I'm sorry, this is not COVID. I managed to choke on water. Sorry. Yeah, I'm just wondering, this transformation from depth to breadth, is this you've done it manually just for those benchmark queries that you've been trying, or you have a systematic translation, say from some fragment of graph language that would have not unlimited recursion, but a fixed number of iterations of paths into SQL and relational algebra?
Oh, we did it manually. So we looked at the BI benchmark and asked ourselves, okay, let's look at the questions that are being asked here and think of it from a relational perspective. How would we model this in a relational database, just as you would, let's say you learn in a database, of course. And that's how we attacked it. But I see a lot of potential in potentially translating graph queries to SQL as well, because lots of people find it more intuitive to express those queries in graph languages. But we know that relational operators scale incredibly well. So why not translate it for the users in cases we can, but in the cases we can't, those queries will likely not scale.
I have a related question. So when you materialize this path, how much is the impact on the write throughput?
Oh, I do not remember the numbers on the write throughput. I do not believe. Oh, I'm sorry, I cannot answer the question, but I can, like, if I were to guesstimate, the thing is, if you were to insert the comments one by one, the whole cost is to find the parent comment that's already in your database, and it's just an index nested lookup, and just take that parent. But we do bulk inserts, and in our bulk inserts, we essentially do recursion to compute all the parent comments before the processing, which of course potentially slows down your bulk inserts, but the queries use these traversals so much that it was totally worth it. I can't like give you the exact numbers off the top of my head right now.
Yeah, so if I understand correctly, so this is a specific design for BI workload, and you store the edge as the table, two-column table, source target.
Yeah. And
the traversal is done by drawing the edge table with the source vertex table and the target vertex table. Okay. So what's your intuition that relation database can handle graph, or your intuition is mainly for BI workload, and you can achieve the scalability by the breadth drawing? Can I say this? So navigation query, you also agree relation database algebra will not beat a native graph engine. Do you agree with this comment?
So a relational database in our, like a relational database, so
relation algebra will not beat graph navigation engine.
So relational algebra with certain extensions, such as recursion, is able to execute many of the same operations that a graph database can. And if those operators are implemented really efficiently, I believe that they can certainly match graph databases. But of course, specific algorithms for certain specific graph operations, such as multi-source, multi-destination shortest path, a proper native implementation is really hard to express in SQL and then like compile to like the similar assembly. So graph databases certainly have advantages in graph workloads, but my intuition is a graph database in many cases to compute the joins, it also does a join, just like a relational database system. So I feel that the approach of starting with the relational system and extending it to handle graph workloads might be just as successful or maybe even more successful, because there's so much research on relational databases already, than going the other way around, starting with like the graph way of thinking and trying to get it as fast as relational systems in relational-like workloads. That's my intuition.
Okay. Yeah, so I can share a little bit what I observe in the real world.
Mm-hmm.
So most people who are using strong type or schemaless paradigm, so all they want is frequent schema change. So they keep adding edge, adding
what change? Sorry,
frequent schema change.
Okay, yeah.
So that they keep adding, imagine a tree. They start with the tree and then they keep adding the leaf and edges and they grow, become a bigger tree or forest. And this is happening a lot. And that's the number one reason that a lot of enterprise are using graph database because they can do a local metadata change and my existing workload does not change. Because my existing workload is to target the existing tree. And then if I grow the tree based on my metadata, my new query can just chime in and traverse from the new edge leaf, new leaf until the entire tree. So I really thought the relation database can handle ever-growing schema metadata.
So is change in schema, thinking in the relational sense, is of course like a big thing for relational database.
Yeah, keep adding edge table, vertex table, and then if I do the new workloads, you're starting from the new edge table and vertex table, and how do you guarantee the performance?
So a relational database system, as you said, stores the edges as relations, so like start and end, maybe additional data information on the edge. And if this edge table represents just a tree, like adding more edges to it to make it a graph or a more complicated graph, like it's not a schema change for a relational database. But of course, adding a new node type, like if we have persons, but if we added professors, like if we are storing a university database, that certainly like is a new operation. But I don't see why relational databases would be disadvantaged in that case, where we like add a new kind of node, like it's just a great table and you add the data, it has great statistics, and then we start joining it with all the other relations. So like if we view the schema as the kinds of joins we do, then like a relational system is just as flexible. You can do more joins, less joins. That's your query in the relational database sense. So you define your graph within the query is how I would think of it in a relational sense, but that's my intuition.
So my intuition is there are many research centered around scale the permutation of large number of join tables. So when you go beyond 22 tables, so the optimizer can go thousands seconds to get the optimal.
We handle that greatly. Like we have great research papers, adaptive optimization of really large join queries that can handle up to 10,000s easily. Like that's not say like pretty well. Our optimizer, it has three different approaches to do this. So join ordering is NP hard, like you can't escape from it, which is the same for everyone in a sense. But what we do is we do this fully exhaustive enumerating DP algorithm, which is quite optimal among all possible DP algorithms that doesn't recompute the same result twice. Like we have this DP algorithm that is super fast, but it can only do up to 20 relations, but it guarantees to find an optimal result given your cardinalities. If we have more than 20 relations, or we have a heuristic where we switch, so we switch to a more complicated algorithm, which uses the IKKBZ algorithm to linearize your query graph and then do a DP algorithm like the matrix chain multiplication to essentially take the left deep tree given out by the IKKBZ algorithm in polynomial time and converted it to a Bushy tree in polynomial time as well. And this takes around, our implementation's complexity is n to the power 4, so can handle up to 100,000 relations. And then we have a further implementation which does a greedy operator ordering with some dynamic programming in for the smaller subtrees, which can handle up to 10,000s of relations. So we don't have a problem with this,
Okay, quick question from Alistair.
I want to go back to what Leonard was asking, because if I understood correctly, you're saying, if I know about queries, then I can change the physical model to optimize. And I need to know about the queries in order to achieve that. So, and that's not, you know, it's not the same thing as knowing, you know, the physical model a priori, and then the optimizer just works off that and the statistics. It's a different thing. That doesn't mean it's wrong. It just means it's different. So it's kind of interesting, because then you need some sort of bank to learn from of queries in order to actually figure this out. If you want to do the automation that you're talking about in terms of of moving from a hand crafted physical model to something that is actually derived in a more general sense. And so, I mean, that's an observation, you know, it'd be interesting on your comment. The other point, it seems to me, is I think this is a kind of sterile debate between quote graph and quote relational. They are different models operating at different levels of abstraction. People want to think at the graph model, and ultimately the job of database vendors is to stop them worrying about how that was implemented, is my view. And therefore you can have that war between different implementation approaches. It's a very important one at another level, but I do think that this is not about graph versus relational. It's about how to best do graph, as well as doing relational if that's what you want to do, which we already have.
I definitely agree, but I see also some difficulties, like looking at queries and then picking the optimal storage. It's incredibly difficult. And essentially forcing the user to use SQL and express the queries in a relational manner forces them to give us queries that we can execute quickly, which is not optimal. Like, you would want the users to express the queries in their own ways. Like, this is in a machine learning library, people would love to compute many things with for loops, but they force them to use these vectorized libraries. Why? Because it's faster to execute and hard to convert that for loop to the vectorized version. So essentially kind of forcing the users to express their queries in a way that's easy to scale. I also see some practical value there, which can make our work easier. However, there is still quite a lot that we can do on our side to allow the user to express their queries and optimize their queries. So for example, some manual improvements we did some manual improvements in common subtree elimination in our queries. This certainly does not have to be manual. An optimizer should certainly be able to do this. So in a sense, I might look at the different optimizations, and for some I might say, oh, it would be much easier if we made the user do this, like a schema change. But for some other improvements, I might say, oh, we could totally make the optimizer do this. So unless there comes out some cutting edge research about how we might remodel the queries, it's quite difficult, because like the optimization that I showed you here, it only works if the comments are a tree and we don't have any link cut operations. Who knows this? Only the user knows this. Or we must make the user express that like in weird ways, or this has to be a tree, but then we have to check it. Like if the user says this has to be a tree and adds an edge that makes it not a tree, we must check it or do something like primary key. So like,
why can't the user express a natural graph approach to expression?
So the question from Alistair is, why cannot the user express these constraints?
What I'm saying is, use a graph express
certainly.
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 And then you get a bank of experience. This is how orthodox. It's not what we have to do in SQL with SQL data. But at least it gives you the starting point for then optimizing of those queries in terms of the schema, because that's what you're
like, I see a lot of value in taking graph queries and converting them to SQL and looking at those SQL queries to then optimize them. That's super interesting. I haven't looked into that much yet. That's certainly a great research area. Changing the schema, that I really don't know much about, and I feel that it would be super hard, but like optimizing the queries, definitely, we should be doing it.
Okay, we have one more question online and then we have to wrap up. I think this is a very useful discussion about the perennial question on graph versus relational.
Yeah.
But
Sadly,
yes,
I have
everyone,
to catch a
please.
flight afterwards, so email me if you can find me offline. Yeah.
Yeah, just very quick question again related to this transformation. I was wondering if this transformation about posts and forums, is it completely automated, or does this need to be done at like the application level?
No, the transformation that I showed is a manual transformation we did while rewriting the queries in SQL. It wasn't an automated transformation. So we do some as Tiger Graph mentioned, there are some pre-computations we do in queries 4, 6, like we do almost the same pre-computations they do. Those pre-computations that we do, and also that transformation that we did, those were done manually by hand.
I meant at the data level. I thought at the data level, you are adding the direct relationship between each post and forum.
Yeah, we get the same data. Like we get a CSV, then run a SQL query to do that transformation and store the results with the pre-computations. We wrote that SQL query, but the system automatically executes that SQL query. And the cost of computing those additional columns are within the pre-computation costs, so they will be visible if and when our results get audited.
Okay, got it. Thank you.
You're welcome.
Okay, so we have to wrap up.
All right.
Yeah, we have to wrap this up. Thanks again, Altan, for the very interesting talk.